Alright, welcome to our first video of Unit 8, this unit's on kinetics. So to start with, we're going to talk about what reaction rates are and actually relate that to what we call collision theory. The rate of a chemical reaction, sometimes though we just call that our reaction rate, is our change in amounts of reactants or products per unit of time. Now this basically lets us know how fast a reaction is going. We measure how fast a reaction is going by basically figuring out how fast we're using up our reactants, or more commonly, how fast we're actually producing our products. So either way, reaction rate is basically the rate of our chemical reaction. It's how fast our reaction is proceeding. Reaction rates are typically expressed in molarity per second. They're often in some kind of solution, and they enable us to basically recognize and determine how the concentration of each of our substances change per second. So again, the higher the reaction rate, the higher the concentration change we have per second. So reaction rates are measured in molarity per second. And just to remind you, molarity per second will be like this. Every now and then, you'll see it like this. This -1 is referring to 1 over S. Normally, it's like this. Sometimes we'll write it like the right. Honestly, if we're kind of low on room and we're trying to write it on one line instead of two. So, both of which are basically saying the same thing. So, that finishes reaction rates. I know, pretty quick. But now we're on to collision theory. A model called the collision theory model is used to relate the properties of particles to our rates of reactions. Basically, we're trying to figure out what about the reactants that we're using causes them to react, and in essence, how can we use that to make them react faster? So, let's talk about our collision theory. The collision theory states that particles must collide with enough kinetic energy and with the proper orientation for a reaction to occur. This means that particles have to hit hard enough and at the right angle to actually cause a reaction. Let me give an example. Let's pretend that we're basically at an archery field. Okay. The collision theory, in terms of archery, would state that arrows have to hit the target with enough force and at the proper angle for it to actually stick in the target. Now, let alone actually hit the bullseye. So that basically means that a good arrow shot, if you will, would be shot, hard enough force, and stick in the target. Okay, however, let me give you an example. If we don't have enough force, meaning in the archery sense, I don't actually pull the bow back enough. In a chemistry sense, if I don't have enough kinetic energy. So again, if they're not hitting hard enough, it'd be like the arrow going, boom, and not really doing anything. Or maybe it would, you hit up and it kind of doesn't really stick in. Okay, it just kind of bounces off. It's not really actually even happening. Now, so that means that without enough kinetic energy, a reaction won't happen. Now, the orientation part is referring to if we had an arrow that is just completely shot the wrong direction. Now, I'm not honestly really sure how you could even get this done. But if you hit an arrow and it hits like backwards, or somehow it just like flops, and I'm trying to rotate, it's not working, and just hits the wrong angle, you're not going to have a reaction. And in chemistry, if the molecules don't hit in the right spot, they won't react with the right atoms, and a reaction will not occur. So again, kinetic energy and orientation. The minimum energy required for a reaction to actually occur is called as activation energy. We also think of that as how much energy you need to activate the reaction, to start it, to get it going. So again, minimum energy for a reaction to occur. Sometimes we also think to start. It's called activation energy. Typically, energy profiles are used to actually reflect the progress of a reaction. Now, we've talked about reaction rates. We've talked about how they measure reactants produced into products. We talked about collision theory. talking about how atoms have to, basically molecules have to hit hard enough and at the right angle. Now, there's kind of one more thing we're learning, like their energy profiles. They're basically used to kind of demonstrate really this progress, if you will. So, energy profiles look like this. Okay, the y-axis represents our system's energy, meaning the higher up we go, the more energy we have. And the x-axis represents the progress of the reaction, meaning we basically start here, and as we go, we kind of move to the right. So we start at this energy level, the reaction increases, and then the energy drops, and we end down here. So energy, reaction, progress. The far left point on the profile represents the starting energy of the reactants, and the far right point on the profile represents the ending energy of the products. Meaning, we start, in this case, higher in our reactants than we end up. So we end up overall kind of losing a bit of energy, if you will. I mean, I know we've got this huge spike, but they end up kind of lower. So, kind of weird. By the way, whenever our products end up lower than our reactants, we call that exothermic. And if, for example, our reactions ended up being lower than our products, it would be endothermic. And this kind of shows us sort of how we end up getting energy. And we'll talk a little bit more about this later. Finally, the difference between the energy of the reactants and the highest point on the profile, which in this case is that, represents our activation energy. Remember, we already talked about that. So this basically says that until we gain this much energy, we can't start a reaction. So if I only gain this much, we're not going to have a reaction. If I only gain up to here, we won't have a reaction. Collision theory says you have to have enough energy. Once you have enough energy, then your reaction starts using up that energy and ends up actually using up a little bit more than we started with. And you eventually get to the point where it kind of is finished and you have your products. So activation energy, again, system energy, reaction progress, reactants, products, activation energy. Any difference between the reactants and the products, which in this case would be represented by this distance. Sorry, it's kind of weird. That's our actual energy change that occurred in our reaction. We commonly call that our delta H. So it's the difference between reactants and products. In this case, it would be a negative number because our reactants lost energy. It does come back to products minus reactants, and that's our delta H. So from this graph, we can actually get an idea of reaction rates. We can figure out how much energy we're required. We can have an idea of how slow or fast it goes by how spread out the graph is. We can look at our kinetic energy that we need to start it, our activation energy. You can get quite a few things from energy profiles. Alright, so for the provided energy profile, which looks like that, and yes, you can have multiple humps, label the following. The two axes, which are the top up and down one, and the side to side one, commonly called the y-axis and x-axis. Where are the reactants? Where are the products? What represents our activation energy? Don't worry about telling me the number. Just show me basically this difference of height or somewhere is activation. And overall, what represents our delta H? Work on that. Come back in a bit. All right, welcome back. Our two axes are our system's energy and our progress of our reaction. Our reactants and products are right there. So we have reactants on the far left, products on the far right. Our activation energy would be that difference. Actually should have been a little bit taller, but from that top point to our reactants. And our delta H, I'm going to draw that in a little different color, would be right there between our products and our reactants. And as you can tell, I can draw really straight lines. Hopefully you get the difference or the idea. But there you go. That sums up reaction rates, collision model, and even a little bit on energy profiles. Thanks for watching.